Today we will implement a maze generator in a two-dimensional grid that works by having a tile that navigates the two-dimensional array, tearing down walls in between the different tiles where it navigates. Here you can see it as a red agent that is just moving around the two-dimensional space, and it is guaranteed to visit every single tile at least once. This video has been inspired by Daniel Shipman from the Coding Train, where he implements a similar algorithm. The resource will be in the comments of this video. Let's get started and implement this using Python and pygame. Our program will be divided in three different sections as usually is. The modules, which includes the libraries, and in this case we're gonna import the pygame library and the random library. Next, we will need the definitions of data. The most important one is going to be the resolution, which determines how big each of our tiles is going to be. Let's try 64 pixels. Then we're going to create a certain number of columns and rows represented with a tuple. How big the two-dimensional grid is going to be. Let's make it 30 by 30. And then we will create a screen. A screen is also a tuple that contains the number of columns multiplied by the resolution to transform the number of columns into the width of the screen. We do the same with the second index, which represents now the height. The next step is to create a screen using the pygame library, display sublibrary, and the setMode method. SetMode creates the screen by receiving a tuple that represents the values of width and height. Now that we have the display, it's time to create the basic unit of information in the system. In this case, it will be a tile. A tile is an instance of a class with the same name, and it represents a square in the screen with walls. The walls are going to be the four types: right, down, left, and up. Let's start with the constructor for this tile. The constructor will receive, as any other two-dimensional grid system receives for their tiles, a position C and a position R, which represents the number of column and the number of row. We are going to register these values as attributes by keeping the same names. Self.r equals R. And then let's think about the position in X and the position in Y. The position in X is calculated in a similar way as we calculated the width and the height of the screen. We take the value of the current position in C and multiply it by the resolution. By doing the same for the rows, we calculate the position in Y of the tile. Then let's add a color. Let's start with a simple white color, or maybe this background color that VS Code has. Let's create the rect component. The rect is the object that actually represents a square in the screen. It is created by putting the position of the top left corner where that square starts, how much to the right, and how much down we're going to move in order to specify the area in which that rectangle lives. So notice, this rect component or hitbox is the physical space of our tile, represented as a square with two main properties: a position and an area. Let's create now the walls. The walls will be represented by a list where every item will be an integer restricted to values between 0 and 1. When the values are 1, we have a wall. In this nomenclature, we will use the same nomenclature that other videos have used: right, down, left, and up, moving in a clockwise direction always, starting with the right direction. Let's create the helper functions that we will use in this program. The first one is draw tile. Draw tile has one job and one job only, that is to draw a rectangle in the surface known as display with the color that we specified for this tile in the constructor, and in the area known as self.rect. This is going to give us a solid square. Let's create a second helper function called draw walls. And draw walls will draw each of the walls depending on whether or not they are up or down. So we are gonna need 4 cases. Case number 1 is right, down, left, and up. In the case of right, we need to ask a question. If the value of self.walls at index 0 is true or equal to 1, something that we can calculate by using the casting method, by turning a number into a boolean, where every number that is different than 0 will give true. If the value is 0, it will give false. So if there is a number 1, or at least any number different than 0 in the first position of the list self walls, we know there is a right wall there. So let's copy this and let's paste it down below a couple more times. I'm just gonna paste it here. This is 1, this is 2, and we have 3 for up. Okay, so if the answer is yes and this wall is up, we need to draw it. We say pygame dot draw dot line, and the line will be placed at the display surface with the color, let's say white, and we need 2 coordinates. The first one is the point of origin of the line, and the second one the ending point of that line. So if this is a line that goes from the right, it means that we need to go from the top right corner to the bottom right corner of that tile. So it means that we need to take the position in the x-axis and add to it the resolution to go to the right corner. And the position in y will give us the top side of the tile. We need to go to the bottom right, that is self.x plus res, comma, self.y plus res. Let's implement the same idea for the down direction. In the down direction, we are going from the bottom left, which is .x, self.y plus res, to the bottom right direction, which will be self.x plus res, self.y plus res. Let's move to the left direction. In the left direction, we are going from the top left corner, which is self.x, self.y, to the bottom left corner, which is self.x, self.y plus res. And finally, the up direction. In the up direction, we want to go from the top left corner, which is self.x, self.y, to the top right corner, which is self.x plus res, self.y. Now that we have the basic unit of information in the system, let's create the next aggregation of these items, which will be a row. A tile row is made out of tiles. How many depends on the parameter dimensions and index 0, because a row is made out of a certain number of columns, and this represents a row of tiles in the system. The tile row will start empty, and we are going to populate it procedurally. That means using a for loop that will go through every single column in a range of values that goes from 0 to the total number of columns that we want. In here, we will apply 2 steps. Number 1, create, in which we create a tile at the position C and 0 in the rows, because we want the rows to be constant right now. We say tile row dot append, and that is the second step in procedural generation. Save the information that you created inside a container. Notice that the tile receives the variable c from the loop variable in the for loop, and therefore gets updated from 0 to 1 to 2, etc., making sure that the tiles are adjacent to each other but they don't overlap. Now that we have the tile row, let's create a template. The template for tile row. The best way to go through every item inside of a list is with a for loop. Because the tile row is made out of tiles, we call this a tile. For every tile in a tile row, we do whatever we want to do, but we do it to a tile. There we go. Now let's create the next level of organization in this system, which is the grid. The grid will be a list as well, but it will be a list made out of tile rows. It is a list of lists, and the number depends on how many rows we want it. It represents a 2-dimensional array of tiles. we populate it procedurally. The grid starts empty. And for every single row in a range of values that goes from 0 to the number of rows that we want, -1 because we start counting at 0, we need to first create and then append. We know that to append, we need to take the list that is called the grid and type append and append a tile row, because it is the tile row that is included within the grid. It is a list of tile rows, so we know we need to make a tile row. The question is, how do we make a tile row? If we look at line 42, we'll find the data definition that tells us how to make a tile row. And here we see the example that generates a tile row procedurally. We'll simply copy this and paste it in line 59. There it is. And we fix the indentations. This data definition grid will also have its template. The template for the grid is done by using also a for loop. In this case, the elements that make the grid are tile rows. So we're going to call this a tile row. For each tile row in the grid, we can do anything we want, but we need to use that loop variable name, which is the tile row. The tile row itself is a compound, so we copy the template for the tile row and we paste it down here. We fix the indentations whenever required, and we have a hybrid template. This right here will be the most important piece of information in our entire program. We're almost ready to start. One of the most important elements we're going to need to include is called the stack. The stack is a collection of tiles that contained all of the different tiles that we have seen so far. It represents a collection of tiles for the current tile to look into. The stack will start empty, sort of. We're going to need to create another data definition representing the current tile. The current tile is that red agent that you saw during the animation. CT for current tile is simply going to refer to an item inside of this grid, represented as a particular row and column of a grid. It represents the agent that travels across the grid, tearing down walls and making it a maze. CT will start anywhere, and in our case we're gonna pick the first tile in the first column and the first row. This tile will contain now a special parameter that is a boolean and will represent whether or not we have visited this tile already. We are going to include CT inside of the stack. Scrolling back up in the data definition of the tile, we're going to add this additional parameter. Cell.visited will start as false. CT will therefore be considered visited. Let's get started with the coding process. Those are all of the parameters and variables that we need in their data definitions. Let's start the coding process. Let's first visualize the grid. Let's start with two functions called draw and update, which we are already familiar with. Let's run these functions forever using an infinite loop. The draw function is in charge of rendering pixels. That's its only job. So we're gonna call for the surface display and the method fill to select a background color. We're gonna select the same background color as the color of the background in VS Code. We then need to do something that allows us to render the tiles, and then we're gonna extend a handshake to ask for pygame to request to the programming language that actually renders the screen to do so. This is done using the flip method. To render our grid, we need to follow our template, the template for the grid. I'm gonna simply copy the template and I'm gonna paste it in line 87. I fix the indentations, get rid of the comments. And in this case, I'm not gonna use this. This one is used to transform the line 89 and 90, these two last sections, into the structure of a helper function that is gonna be called here, and it will consume each of the tile rows. However, in this case, I want to do things the long way. Here we have the tile, and the only thing we need to do in order to draw the tile is to find the method that will allow us to do so. We have two, draw tile and draw walls. Let's draw the tile first. Let's fix the indentations once more because I see that there is some empty spaces that shouldn't be there. I press Alt Shift F and it gets fixed. Let's run it and let's see what happens. Okay, oh, it works. I am not able, however, to move the window or do anything else. And the reason why is because, first of all, the window is extremely big. I made it too big. So I need to reduce the number of the dimensions. I'm going to make it 15 by 15. And I'm going to make them of, maybe I'm going to keep them of 30 by 30, but I'm going to make them 32 by 32. Let's run it once more, and we have our window right here. But still, I can't move it around. That is because our window is not interactive. To transform our window into an interactive window, we need to go through every single event in the list of events of pygame that we can access using the get method. And we can ask if the event is of type quit, which is a constant that pygame has. And if the answer is yes, we exit the game. This alone will allow us to move the window wherever we want it to go. And let's make this, let's keep 32 and let's change the dimensions to 20 by 20. It was still too big, I couldn't see it all. There it is. Now we can move our window around and we can even close it, everything's fine. Let's draw the walls. If I decide to draw the walls right after I finish drawing the tile, some unexpected consequences may appear. The most notorious one is the fact that some of the walls will be hidden. And the reason why they're hidden is because the tiles that came after just get rendered on top of the outlines that we had drawn in the previous iteration. To fix that, we need to just use the for loop again using the grid and repeat the process. But instead of calling for the draw tile, we call for the draw walls. And this time, whoops, it seems that we still have an error, and I'm pretty sure I know where it is. It is right here, line 69. So something that I forgot to mention that was very important is that this element C should be accompanied now for the loop variable R, because R is the loop variable that represents the changes in the rows. If I keep this at 0, all of the tiles in the grid will be overlapping one over the other in the first row. Okay, let me run it once more, and we have our two-dimensional grid. Fantastic. Let's now start the process by which we are applying the forward step, which we can call the exploration stage, and also the backtracking. To explore the canvas, we need to evaluate the number of neighbors. So we need to get a list of valid neighbors. Valid neighbors will be equal to the output of a function called getNeighbors that will receive as an input the current tile. This current tile will need to be modified later inside of this function update, so I better make it a global variable. I'm gonna go before the update function and I'm gonna create the second function, getNeighbor. We receive CT. So we need to ask if there are neighbors to the left, neighbors to the right, neighbors above, and neighbors below. If the answer is yes, we need to also ask if those neighbors haven't been visited. If the answer is yes, and these neighbors haven't been visited, and they exist, we are gonna append them and we're gonna return them. So we're gonna create a return list that is gonna be called simply the neighbors. And it's gonna start empty. We need to check in the right direction, down direction, left, and up. We first are gonna ask if the value in CT of C is bigger than the total number of columns minus 1, because we want to look at the item to the right. Oops, sorry, not bigger, less than. If the answer is yes, then we can ask if the neighbor to the right, which would be at the grid position in the current row of CT and the column to the right, hasn't been visited. Something we can ask by adding the not logical operator. There it is. If it hasn't been visited and CT is not in the last column, -1, we still have neighbors to the right, so we can append it. So we can say neighbor.append, and we just need to append this element right here. There it is. Let's complete the other ones. Here we have the second case. In this case, it's not C but R, it's not dims at index 0 but 1, and instead of ct.r is ct.r plus 1 and ct.c. We copy this one and we paste it below. Let's work really quickly through the last two. So this one involves C, but this one will only ask if it is bigger than 0, which means starting at 1, so we can check for the neighbors to the left. So we're gonna respect the position C, we're gonna take C minus 1. And this is the element that will replace the items below. Here it is. Now we have this, we just need to ask for up. If the value in the row is bigger than 0, and r minus 1 and ct.c hasn't been visited, then we append it. Those are the 4 cases. Once we have them, the only thing we need to do is to return that list of neighbors. And now we have the list of neighbors. So what else do we need to do with that list of neighbors? The next thing is to pick one of these neighbors at random. First, we ask if the length of the valid neighbors that we got back is bigger than 0, it means that there is at least one position where our agent can move to. So we just pick randomly from those. And we need to make sure that we have the random library. We do, it's right there. So we can proceed. So chosen will be equal to a random choice of the valid neighbors. Once we choose that tile, we are gonna tear down the walls in between the current tile and that chosen tile. So we're gonna call a new function tear down walls. This one will receive CT, which is the current tile, and the chosen tile. Once this is done, we need to make sure that the status of the chosen tile has been visited, which means that we won't consider this tile anymore in further iterations of the algorithm. Okay, so once we change chosen to visited, we also need to update the current tile to be equal to the chosen tile. And we need to add the chosen tile to the stack. Let's work on this function tear down walls. We have CT, which is the current tile, and then we have CH, which is the chosen tile. So we have 4 cases. The neighbor, the chosen neighbor is to the right of the current tile. The other case is when the chosen neighbor is below the current tile, when it is to the left, and when it is up. If the chosen tile is to the right, that means that chosen's position in C minus the current tile's position in C should be positive, which means it's bigger than 0. Then we tear down the right wall of the chosen tile, which would be the index 0, and we make it equal to 0. And we tear down the left wall of the chosen tile, which would be the index 2, right down left, 0, 1, 2. We set it to 0 as well. Let's work through the down case. If the chosen tile's position in R minus the current tile's position in R is bigger than 0, it means that the chosen tile is below the current tile. So we are gonna set CT walls at index 1 equal to 0 and ch.walls at index 3 equal to 0. Let's work with left. If the chosen tile's position in C minus the current tile's position in C is less than 0, we set ct.walls at index 2 equal to 0. And we're gonna set ch.walls at index 0 equal to 0. Notice here that this pattern is the reverse of that one found at the beginning when the pattern was to the right. So that can help us assume that making the up direction will be quite simple. We just need to ask if the position in the row CH minus the position in the row CT is less than 0. And if the answer is yes, we just need to flip down. So this one will become a 3 and this one will become a 1. That's what should tear down the walls. Okay, let's run the program and let's see what happens. Okay, but something is definitely going on. That's great, but it's really hard to see. Let's do two things. Let's define the color of the tiles based on whether or not they have been visited, changing the color of those tiles who have been visited, and let's make the tile that is leading the way a different color. Let's do it here in the update function. Let's take the template for our grid, which is down here. We copy it, we paste it down below. Then we fix the indentations and get rid of the comments. There we go. And this time we will ask if the tiles state visited is equal to true. If the answer is yes, we change the tile color to be, let's say, green. However, if the tile is equal to the current tile, then we also change the tile's color to gold. And it works. The random behavior that plays a role in the selection of the next tile where the golden tile is gonna travel gets sometimes stuck because there is a point where that tile doesn't have any neighbors that are available anymore. To fix that, we need to implement the backtracking. So that's what happens here. If there is no valid neighbors around, we need to ask if the length of the stack is also bigger than 0. If the length of the stack is bigger than 0, then it means that there is at least one tile that we can go back to and then ask the question as to whether or not that tile still has neighbors available or not. So we can pick the CT to be equal to the member of the stack at the index -1, and then we can remove that element from the stack by using a stack.pop at index -1. That should make sure that the current tile goes back to the previous tiles it visited and reformulates the question, but doing it only once. When we run the program this time, the two-dimensional grid gets transformed into a maze. This maze has the nice feature of always being solvable. No matter where you start in the maze, there will always be a way to go from the top left corner to the bottom right corner. Let's change the color of the walls. Let's make them red. Maybe that will be a little easier to see. And there it is.